Okay, so hi again, everyone. Welcome to our Wednesday seminar. Today we have the pleasure to hear from Tatiana Pavlidou. So I'll say a few things about Tatiana. So Tatiana is currently a postdoctoral fellow at the University of Vienna, working with the Nemesis team. And she is developing machine learning techniques to identify young stellar objects with big data. And so Tatiana obtained her PhD from the University of St. Andrews in Scotland, where she worked with Alex Schultz. And after that, she moved for a while as a research, she worked for a while as a research associate at ESO, where she did various machine learning big data projects with the ESO archive. And so today, she's going to talk to us about star formation in the Perseus complex. So Tatiana, thanks again for joining, and the floor is yours.
Great, thank you very much for the introduction, and thank you for having me. And also to everyone for joining and being so patient. So yes, today I'm going to talk about star formation in the complex of Perseus and effectively try to show multi-wavelength study. As already said, I'm part of the Nemesis group which is a collaboration between University of Vienna and the University of Geneva and Konkoly Observatory in Budapest. And the group is, just to clarify, is really aiming into building machine learning techniques and to identify and classify young stellar objects, but I'm not so involved with the machine learning aspects. Okay, so I should start by, okay. I'm going to divide my talk into two sections. In the first, I'm going to talk about the general stellar populations of the Perseus complex, which is what I did effectively in my PhD thesis, and for which I used Gaia data, Spitzer, Weiss, Thomas, and Planck. And then I will move on to the second section where I will cover my current work, which is about the class 0 population of this complex using Herschel and Spitzer data. So to start with, I thought I would say a few things about why we care about stellar clusters. And I'm sure many of you have heard and read that these are the birthplaces of stars, and therefore they're important in understanding in star formation in general. And since they're groups of stars with many common properties, by looking at these regions, we can minimize a lot of biases, metallicity biases, also extinction biases, etc. And they're also inextricably linked with the initial mass function, which is the mass distribution of a cluster at the time of birth, in theory. And this is a very important initial condition for simulations. And here, just to
interrupt, Tatiana, if you're scrolling through your slides, we're still seeing your title page. So what you're sharing is not your. I think it's the wrong window. So do you want to stop sharing?
Yes, thank you. I was already in my third slide. Okay. Let me stop sharing. And okay, can you see it changing now?
Yes, yes.
Yes, thank you.
All right, great, thanks. Okay, so as I was saying, for stellar clusters, the initial mass function is it's an important initial condition for simulations. And here I thought I would show just an example of how this initial mass function changes from Paduan simulations in 2004, according to a different Mach number, which is basically a measure of how important the pressure forces are in a molecular cloud. And then finally, there is a newer motivation to revisit stellar clusters from Gaia DR2. And that's because with Gaia, we got highly accurate proper motions of stars, which is a very crucial criterion in order to establish membership into clusters. And really with Gaia, it became not just interesting, but also necessary to revisit many star-forming regions. Okay, and then why do we care about YSOs? Well, we have been trying to understand how stars evolve for a long time now, and here I'm introducing the classification scheme, which was first proposed by Lada in 1997, and it effectively describes how a core, an embedded core, starts to evolve into class 0, class 1, 2 and 3 phases. So I'm not going to go through the whole phases here, but I want to say that there are a few difficulties that come with this classification, and one of them is that we often rely on bolometric temperatures, and these estimates in turn rely on trustworthy SEDs, which we often do not really have because we need extensive wavelength ranges. So there is often a bias towards regions that have been studied by multiple surveys, and therefore we can build such SEDs. So the general aims of my current project with Nemesis is whether we can find a way to distinguish between class 0 sources and class 1 sources in particular. And also I'm becoming more interested in whether hot Corino sources relate to this star formation picture. And to introduce hot Corinos, the first one reported was the Iris foray in NGC 1333, so in Perseus. And this was, Iris foray is a low mass protostar, and in fact it's a multiple system. And what it was found from Bottinelli in 2004 is that this low mass protostar exhibits a rich spectrum in complex organic molecules. And many hot Corinos have been discovered since then. And the way we define them is that they're basically the warm inner envelope of low mass protostars. So they have high abundance of methanol, H2CO, and H2O, and other hybrids. And they're generally cold at about 100 Kelvin. So moving on to the stellar populations that I explored during my PhD, I thought I would start by saying what we knew about prior to Gaia. And Perseus has always been this very interesting region because it's, well, nearby at 300 parsecs. It hosts two main clusters, ISO348 and NGC 1333, but also a dispersed population of young stellar objects. So it has been always this great laboratory to study star formation. And in terms of membership samples, the best to date, it's perhaps the one by Lumen 2016, who did a spectroscopic census of these two clusters. The thing is that prior to Gaia, we had always been restricted by the Spitzer coverage of this region. So everything we really, all the studies that would really look into Perseus would contain this, would be within this white outline that I'm showing here. Then this is a picture from Zari 2018. So then Gaia came, and as I said, with Gaia came a full sky map, which was really important. And of course, also the high accuracy astrometry. So not only positions and proper motions, but also parallaxes. And in addition to optical photometry. So with Gaia, we could really go far and beyond this Spitzer coverage of the Perseus region. And here I'm showing a preliminary sample of Perseus. We can see that IC348 and NGC do come out. And in this sample, I have some conservative cuts, like a 10 million year cut, and a distance range between 230 to 550 parsecs. But of course, there is still a lot of contaminants for the foreground and background. But the nice thing is that if you look at this for a while, as I did, you start seeing structures around the two main clusters as well. So a way to detangle this, I thought, was to create a grid in the plane of the sky and start counting stars in little boxes. And here what we see is basically a stellar density map of the region. And we see that ISO348 and NGC come out, which is good confirmation, but we see that there is 5 additional clusterings around. And the question is, of course, whether these are accidental clusterings or if they're groups of physically related stars. And this is work that I published in my 2021 paper. But just to summarize, in order to test whether these are real clusters, I first select these groups in spatial distribution. I plot them in the proper motion space, and we see that they cluster really nicely in proper motion too. So these are co-moving stars. And they also cluster in parallax. Here, this is parallax error against parallax, and we see that there is for all 5 a parallax mean. So they're also clusterings in 3D, in the 3rd dimension. And then finally, then in CMD diagrams from Gaia, we also see that they follow well-defined isochrones or set of isochrones. So they're groups of co-eval stars as well. So perhaps the best part about this was that I got to name these 5 new clusters. So we have a small one next to NGC. I don't know if you can see my cursor, called the Tochli. On the other side, next to IC348, we have Chaos, and then these 4 lie on the front part of the complex, and then on the back, we have Helios, Electrion, and Mestor. And these are the names of 5 out of the many children of King Perseus in Greek mythology. So, of course, there's a lot of questions that come up. There is now 7 clusters in total associated with this complex, and one wonders whether they're, of course, kinematically related and how. What are the relative ages? Is there like a uniform mass function across these 7 clusters? So to start with the ages, the first indicator that I use is the Gaia CMDs, which I already showed for the 5 new ones. But here we also see IC348 spans a range of ages between 1 and 5. The red isochrone here is 5 million years. The 1 million year isochrone is represented by the orange. And this is for IC348, this is in agreement with literature. We know there is a span of ages between even like up to 6 million years, according to some studies. NGC and Autochthy are coeval at 1 million year. And then the rest, 4 clusters are relatively older, between 3 and 5 million years old. The second indicator I use is to overplot these clusters on a coal dust emission map from Planck data, and this is at 353 gigahertz, and now in galactic coordinates. And what we see is that IC348 and NGC, which we know are star-forming clusters, are coinciding with some coal dust emission, and so does Autochthy. And they're also very compact structures, whereas Helios, Electrion, Chaos, and Mestor are located off the main cloud of emission and are also more spread out distributions. And then finally, I use WISE data in order to get an estimate of how many stars with disks there are in each cluster. And to do that, I use an empirical criterion of K-W2 larger than 0.5, which was motivated by a study in the Lupus cloud by Teixeira 2012. And when we plot the disk fraction of these clusters from WISE data against the cluster age we get from the Gaia CMDs effectively, we see that NGC and Autochthy have the highest disk fractions, and they're followed by ISO348, which has a big range of ages again. And then we have separately Helios, Mestor, Electron, and Alkaeus with the lowest disk fractions, which do not differ a lot. So what we see nicely here is that, again, this segregation of where we have the 3 star-forming clusters and the relatively older clusters, which are non-star forming. But we also see this downward trend, which is it's really meeting our expectation, because we would expect the cluster to, as it evolves, to have more and more of its members losing their disks. And this is, of course, not the first time we see this. The first who plotted a figure like this was Haish in 2001, I believe, who did a similar analysis for clusters in different star-forming regions and also observed this downward trend. So the next thing we wonder is whether this segregation between the 7 clusters is seen in other parameters. And I already mentioned a bit about the front and the back clusters. So really we have IC348, NGC, Autochthy, and Alkaeus on the front at about 300 to 310, 20 parsecs. And then on the back, from 350 to even 400, we have the 3 clusters of Mestor, Electron, and Helios. And then in proper motion, we have again 2 clumps here. In one, we have, in the faster one, we have NGC and Autochthy, which move together. And this makes sense because they are very close together and they're also coeval. But they're also moving with Alkaeus, which is located on the other side of the complex, and it's also an older cluster. And then on the slower clump, we have most of IC348 and Mestor, Electron, and Helios. So after that, I move on to getting the mass functions for these clusters. And in order to do that, I use data from 2MASS, and specifically, I convert the J magnitude into a mass using the Baraf models. I only do this for stars up to 1.4 solar masses, and this is a limitation of the model. And here, in the interest of whether we see any mass segregation in the cluster, I plot in orange, there are the sources that are excluded from this analysis for the mass function. And we see that there is some segregation in IC348. So these orange ones here are basically sources that would have a mass higher than 1.4. And then once we have these stellar masses and we plot them in, well, basically a histogram, which is what the mass function is in the end of the day. On the left, I have IC348, NGC, and Autochthy. And on the right, it's Alkaeus, Mestor, Electron, and Helios. And because the samples that I have here are only complete between 0.3 to 1.4 solar masses, I only compare the middle regimes of these mass functions. And what we see is that they do not really differ a lot across these clusters. And what we can say from this is that perhaps the Mach number across these regions does not differ a lot, and therefore the pressure support of the star forming clouds of these clusters were not very different. And trying to understand better the star formation events that happened in this complex, there is a few conclusions that are clearer. And the first is that NGC and Autochthy probably formed together, and that they're in fact part of the same cluster since they're so close in the sky, and they're also moving together. In fact, it's interesting that Autochthy here seems to be a subcluster in proper motion. And they're also coeval at about 1 million year and probably still star forming. And then similarly, Mestor and Electron are also very similar properties. Again, they're coeval and move, have very similar proper motions. So they're at about 3 to 5 million years old, so maybe they have enough time to separate. So they form together, but maybe separated afterwards. And then finally, trying to put these different segregations we see across the 7 clusters in a plot. Here I show the distance to each cluster against the galactic latitude. The orange ellipse here represents the proper motion group that includes NGC, Autochthy, Alkeos, and part of IC348. And then the orange ellipse is the other proper motion group, which again includes Mestor, Electron, Helios, and most of IC348. And this is to show that maybe in a star formation scenario, there were 2 kinematically distinct subclouds. In this scenario, we would have IC348 in the intersection. And this would explain that the fact that we see IC348 star forming for so long and spanning a wide range of proper motions as well. But this is, of course, just a scenario to try and understand the bimodal nature of the complex. And I'll close this section by showing Perseus after Gaia in a glance. So we have now 7 clusters in this complex, and which show this separation in different parameters. And the interesting thing is also that the fact that in the dispersed population, we see something similar as well. So I'm not going to talk a lot about the dispersed population because it's even harder to get the membership of ReLAM members. But if we here in orange, I show sources that would move with this clump over here, which includes NGC, Autochthy, and Alkeos. And we see that they kind of form a filament between these 2 clusters and IC348 and Alkeos here. So there is really some structure. And then on the other hand, in the sources moving in this other clump here, they're more concentrated around IC348 and in the western part of the complex, which would make sense. Okay, so moving on to the second section of my talk about the class 0 population of Perseus, which is my current work mostly. So in order to identify class 0 sources from our current classification scheme, we expect that their SEDs will peak at about 100 micros. And this is because a very young core would still be embedded, and what we would see is mostly the radiation from the envelope around it. Now, the difficulty that we face is that sometimes, depending on the viewing angle, a class 0 source SED could look like a class 1 source SED. And specifically, when we view a class 0 source face on and we get a bit more flags from the core, this can be very similar to when we view a class 1 source edge on. So in order to try and distinguish these 2 classes, I use data from Herschel, which is an ESA mission operating in the far infrared and sub-millimeter. It has 3 instruments, Spire, HiFi, and PAX. I'm currently using data from the PAX instrument, which is basically photometry at 70, 100, and 160 micron. And in particular, I'm using a point source catalog, which was constructed by Martin in 2015, a collaborator in the Nemesis group. And this is basically a homogeneous extraction of point-like sources so that we don't have any galaxies in this sample. And then I combine these with shorter wavelengths from IRAC bands and MIPS bands from the Spitzer C2D survey for Perseus. And part of the motivation to use these two data sets is also a study by Stutz in 2013, where they do a Herschel study in Orion, where they use the flux ratio of 70 to 24 micron from Herschel and Spitzer respectively. And what they do is to use a cut to get a cut at 1.65 to get a list of sources that would basically be Pack's bright red sources. So would have probably zero-like SEDs, since they would probably peak around 70 to 100 wavelengths. And they do feed SEDs to these sources, and they find that they indeed have zero-like SEDs. And I thought this analysis was interesting to apply to other surf-forming regions, but I'm only focusing in Perseus here. And we get about 100 sources that are in both the PACS catalog and the C2D survey, so it's not a huge sample. But when we carry this analysis, we find 12 PBR sources. And I think this is interesting by its own, because in Stutz they find 18 sources, and here, which is a much richer and a more complex region, Orion. So this is comparable actually for Perseus, which is much smaller. And then the other thing we want to know is, what do we find with this criterion? And indeed, we see that for most of these sources, we see that they're class 0 sources. And not only that, but they're also two well-known hot corinos. And I will come back to hot corinos in a bit. We also want to explore how these 12 sources look like in other flux ratios. And here I show on the y-axis the 24:8 flux against the 100:8 flux ratio. And firstly, we see that these two sources have a negative 24:8 flux ratio, so they're likely to have a more evolved core. And we also see that the rest selected PBRs in open circles here, they lie to the right of x=2 line, and so do a few more sources in open diamonds here. And just to explain really what this x=2 line would mean, is that we have at least 100 times higher flux at 100 micron than what we have at 8. And this would basically correspond to this ST shape over here, which would be hard to confuse with a class 1 source. So we probably are really dealing with class 0 sources, or even a bit younger than that. And again, trying to gain information on what these sources are individually. This is still in progress, but most of these seem to be protostellar cores or class 0 sources based on literature. And for others, we might need to get more information either by observation proposals or other literature studies. And to come back to hot corinos, there is a study by Higuchi in 2018 who observed 36 targets in Perseus, and specifically the molecular lines of C2H, C3H2, and methanol. And they find that the hot corino sources have abundant methanol and deficient C2H, which is what we would already expect from what we know about hot corinos. And effectively, a low C2H to methanol column density ratio would indicate a source with hot corino chemistry. So I combine everything in these plots here, and I show on the y-axis the C2H to methanol ratio from Higuchi. And on the x-axis on the left, I show the 70 to 24 flux ratio, the first criterion used. And on the right, the 100:8 micron flux ratio. And what we see, of course, not all of the sources that I have in my samples are found in Higuchi, but the ones that are found and that are found also in Enoch 2009, we see that the selected PBRs are all has 0 sources, and that they also have, most of these have a low C2H2 methanol ratio, so they would likely have a hot chemistry. There's only 2 that are slightly above, but we need to look into these individual sources better, and yeah, there is more work to be done. But this is it for me, and I will leave you with my summary slide and an artistic impression of the Perseus clusters, and thank you for your attention.
Thank you very much, Tatiana, for this very interesting talk. So we have some time for questions, so people can just pick up or raise their hands.
I have a question.
Yeah, go ahead, Costa.
Hi, Tatiana. Thanks for the nice talk. Could you please go to the slide where you show the distances of the different clusters you identified?
Mm-hmm. Well, wait. So the parallax histograms, you mean?
Yeah.
Here.
Yeah.
Yes.
Okay. So my question is, where would the actual cloud be located here? The
Where
Perseus cloud. The gas. Where is the gas?
Well, that's a very good question. So the dense cloud of the region is supposed to be on the front, so that there is no. It's of course hard to put real limits of the cloud, but it's expected to be between 280, I believe, up to 380, 320, 330. There is a paper by Zucker 2020, I think, where they actually they define the distances to many star-forming clouds, and if I remember correctly, is somewhere between 280 to 320 or something like that. So it's where these 4 clusters are located as well.
Okay, thank you.
Other questions for our speaker? So I have a very naive question for you, Tatiana. So how much do you think the final Gaia data release will improve on the results? Will it be helpful, or is there any projection, any?
The final, you mean, so the Gaia DR3 is already out? Is that the question? That
No, I'm talking about the future, the
very final
future,
one. So to be honest, I'm not sure how. I can say what I would like to have. If the parallax measurements would come with a bit lower uncertainties, this would really help, because as you can see from these histograms here in particular, we have a very wide range. So of course, we wouldn't expect the cluster to be, I don't know, like 100 parsecs deep, and this is of course an artifact here. So I guess if we get minimizing the parallax uncertainties, that would be good. Of course, then the second thing would be radial velocities, but I'm not sure how, if this would really become available with future releases. yeah, I think that's the main two things that would really improve, would help us explore more these 7 clusters.
Okay, that's clear. Thanks a lot.
you.
Any final question for our speaker? Going 3, going 2, 1. Okay, if not, then Tatiana, thank you again for doing this talk, and the talk will be online at some point, so I will contact you about that. And thank you everyone for joining, and see you next week. Bye.
Thank you. Bye.
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 Hello, Tatiana. Nikos Kilafis.
Yes, yes.
How are you? Good to see you.
I'm
Thank you.
good. Yes, good to see you too.
Thank you for a nice talk. Very, very clear. Yeah, you have the ability to make everything extremely clear. This explains why there were no questions. Very, very clear. Thank you.
Thank you.
Okay.
Good to see you.
Yeah.